Welcome to Cheenta Statistics and Data Science. Today we're going to solve this problem from IIT JAM MS 2020, problem number 10. The problem says that let x1 through xn be IID random variables having normal mu comma sigma square distribution where mu is a real number and sigma greater than 0. Define w is equals to 1 by 2n square summation I running from 1 to n summation j running from 1 to n xi minus xj whole square. Then w as an estimator of sigma square is biased and consistent, unbiased and consistent, biased and inconsistent, and unbiased and inconsistent. So basically, we have to find out whether W is a unbiased or biased estimator of sigma square, and similarly for the check for the consistency of that estimator, right? So W is nothing but this given 1 by 2n square summation over I and j xi minus xj whole square, right? So just expanding it, just this is nothing but this square term. Breaking out this square term is xi square plus xj square minus 2 xi xj, right? Now, if we take the sum over I and j, this thing, this thing is only dependent on I, right? Summation xi square, not on j. So this thing is going to be when we take this both the sums, this thing is just makes it n times summation xi square, right? This is summation I running from 1 to n into xi square. Similarly, this thing is also n times summation xj square, so j running from 1 to n, right? And the last term, this thing is actually what? This is summation xi into summation xj. That is summation xi whole square. So twice summation xi whole square. This summation terms has to be treated very carefully, right? So this is actually what this is the just when we take both the sums, since this thing is only dependent on I, it actually gets out of the j sums over j. So this thing becomes n in times xi square, right? So but there is obviously the sum over I, so summation I running from 1 to n into xi square. Similarly for summation j running from 1 to n into xj square minus twice into 2 into this thing is summation over xi and summation over I and summation over j xi xj. So basically this is nothing but summation xi whole square, not summation xi square but summation xi whole square. So this thing is this. Now, if you notice this thing and these things are basically same, right? The this is I and j are just the counter variables. This is nothing, just taking j. This is just counts. So this is not a problem. So this term and this term are the same. So it's nothing. So it's actually 2n into summation xi square minus 2 into summation xi whole square, right? Now this is nothing but 1 by n summation xi square adding from 1 to n, just dividing it by 2n square, right? And this is summation xi by n whole square, right? Now this is nothing 1 by n summation xi square minus x bar square, because obviously this term is x bar summation xi by n. So 1 by n summation xi square minus x bar square. Now this thing can further be written as 1 by n summation xi minus x bar whole square. This thing can be written as this, right? If you can just break it down again, you will find out this thing. So not a problem. Now this is nothing but n minus 1 into, we are just adjusting it for something, n minus 1 divided by n into 1 by n minus 1. So basically we are just adding this n minus 1. This is just cancels out. So basically this remains the same thing. This n minus 1 and n minus 1 cancels out. So 1 by n remains the same, but we're just using it. So this is ultimately n minus 1 by n into s square. S square is what? S square is the sample variance. So this entire w is actually nothing but n minus 1 by n into s square. So this is a familiar thing, right? We know that s square is a sample variance. So expectation of w is nothing but n minus 1 by n into expectation of s square, right? Now we know that sample variance is an unbiased estimator of population variance. So we know that expectation of s square is sigma square. So ultimately expectation of w is n minus 1 by n into sigma square. So obviously this is not an unbiased estimator of sigma square. It's a biased estimator. So w is a biased estimator, right? W is a biased estimator of sigma square. But if we take the limit n tending to infinity, expectation of w is actually what? Limit over n tending to infinity, n minus 1 by n sigma square. This is nothing but sigma square. So under the effect of limit n tending towards infinity, expectation of w is sigma square. That's a good thing, because we are checking for consistency. Now the variance of w is actually what? Variance of n minus 1 by n into s square. So it's n minus 1 by n into n minus 1 by n is whole square into variance of s square, because the constant terms get squared out. So this is the square of n minus 1 by n into variance of s square. Then obviously n minus 1 into s square by sigma square follows chi square n minus 1, right? We know that under the assumption of normality. It is normal problem. It is a problem from normal distribution. So this thing obviously follows normal distribution. This chi square n minus 1 chi square distribution with n minus 1 degrees of freedom. So expectation of this thing is 2n minus 1, right? 2 into n minus 1. Now therefore variance of s square is nothing but 2 into sigma to the 4 divided by n minus 1, right? We just did this entire thing to find out the variance of s square because we don't know the variance of s square. So from the distribution of this thing we can find out the variance of s square. It's nothing but 2 into sigma to the 4 by n minus 1. Therefore variance of w is actually n minus 1 by n square into 2 into sigma to the 4, right? Just putting the value of variance of s square here. So now under the effect of limit tending to the infinity, n tending towards infinity, variance of w is limit n minus 1 by n square into 2 sigma to the 4. It's nothing but 0. So limit, under the effect of limit, the variance of w is 0, and under the effect of limit, remember the expectation of w is sigma square, right? Remember, so w is a consistent estimator of sigma square because it satisfies the conditions of consistency, right? So yeah, so w is a consistent estimator of sigma square but not a unbiased estimator. It is a biased estimator. So remember, so it is biased and consistent. So yeah, there you have it, the solution to this problem. It was very easy just to check the expectation and all. The initial part, the initial w was a bit intimidating. It could have been a bit intimidating to some people, but it's nothing but a function of s square, as you can see. So yeah, it was very easy. Do like, share and subscribe to the channel for more exciting problems. See you till next time.